Welcome back, folks. In today's class, I'll be talking about the momentum in one dimension. So first of all, I'll talk about what is one dimension. So on a navigation system or on an XY system, this is x-axis, this is y-axis. If the object is along x-axis or along y-axis, then that kind of a problem is called as one dimension problem. In terms of direction, if the object is moving along east and west direction or north and south direction, so that kind of a problem will be called as one dimension problem. Now we are talking about momentum in one dimension. So to do that, we need to understand conservation of momentum. Conservation of momentum. So before I jump into the conservation of momentum, I'd like to recall the conservation of energy. Conservation of energy. So you might have learned in the conservation of energy that energy is conserved, which means that initial energy is equal to the final energy. Energy can neither be created nor be destroyed. It can only be transferred from one form to another. That is in accordance with the conservation of energy. For example, if you clap, so once you're going to clap, so you are applying kinetic energy into your hands, and that kinetic energy gets converted into sound energy once the hands collide. So one form of energy converted into another form of energy. Another thing, you can take an example, car. In car, you throw in the gasoline, so gas burns and then car runs. So this was the chemical energy of the fuel, which got converted into the kinetic energy when the vehicle starts running. Another simple example you can take is, if the object is placed on this ramp, and this ramp has certain amount of potential energy here, and then once this ball starts moving, that potential energy will convert into the kinetic energy. So that's called conservation of energy. Conservation means whatever the initial sum of the energy was, the final sum of the energy will remain the same. Obviously there are certain losses, we are not talking about the losses here. So same way, the conservation of momentum is. So conservation of momentum means that whatever the initial momentum of the system is, P initial for a system is, that will be equal to P final. Now, generally, when we talk about the conservation of momentum, we talk about conservation of momentum in collisions. So for example, if this is a car which is moving with, let's say, 1000, not 1000, this has a mass of 1000 kgs. This has a mass of 1000 kg and moving with the velocity of 5 meters per second. Another car, this car is moving in the opposite direction, moving with 10 meters per second, again same mass, 1000 kgs. So what will be the like the momentum, initial and final momentum? So whatever the initial momentum of this car before the collision is, you can calculate by P1 equal to M1 V1, and this one will be P2 equal to M2 V2, and you can add these two. That will be the initial momentum. Once they collide with each other after collision, their momentum will be the same. So that's what the conservation of momentum is, that P initial is equal to the P final. So hopefully you were able to understand what's the conservation of momentum is. Now there is a equation we can break down again. We can elaborate onto that. So P initial equal to P final. Now I'll break it down into the momentum and velocity. Initial momentum is equal to M1 V1 plus, I mean, if there are more than one system, like for example, in this case, there was one car here, another car here. So there are two cars in the system. So I'll call it as M1 V1 plus M2 V2 equal to M1 V1 plus M2 V2. These were the initial ones. So I'll put an initial here. This is final. So I'll put a final down here. Now, if there are more than two cars in a system, then what's going to happen? You will write it as M1 V1 plus M2 V2 plus M3 V3 equal to m1 v1 plus m2 v2 plus m3 v3. And this is the final, this is final, this is final, this was initial, and this one is initial. So that's how. And if there are n number of systems, so then you will write down this equation n number of, with the n number of uh, n number of m and v. So now let's look into a problem based on the concept which we've learned. So this is the question given to us. A 75 kg hunter, in a stationary kayak, throws 0.72 kg harpoon at 12 meters per second. Right, the mass of the kayak is 10 kg. What will be the velocity of the kayak and the hunter uh, immediately after the harpoon is released? So if this is a kayak, this person is sitting in the kayak, he throws a harpoon in the forward direction, and obviously if he throws the harpoon in the forward direction, this kayak will move in the opposite direction. Now we wanted to find out what will be the velocity of the kayak and that person is, because that person is sitting in the kayak. Now let's write down mass of the harpoon. MH is given to me 0.72 kgs, and I'll call it as M3. Harpoon as 3, and M1, I'll call it as the mass of the person, which is 10 kgs. 10 kgs, and the mass of the kayak, I'll call it as M2, which is equal to well, person's mass is 75 kgs. So M1 is 75 and the kayak mass is 10 kgs. Okay. And what else is given to me? The harpoon has a 12 meters per second to the right after he releases it. So he throws the harpoon at 12 meters per second. So because if he's throwing means after the collision. Before throwing will be before initial momentum, and after he throws that moment, because now the harpoon and the person is segregating once he throws it, they are two different identities. So I'll use this velocity as v2 final as 12 meters per second. This is to the right, so I'll keep it as positive. Now I'll write down the equation, standard equation which we learned. In this case, how many identities are there? One is person, another is kayak, third one is harpoon. So m1 v1 plus m2 v2 plus m3 v3 equal to m1 v1 plus m2 v2 plus m3 v3. Again, this one is initial, this one is initial, this one is initial, this is final, this is final, this is final. Now if we are given the different identities, we will use them. So m1 is initially mass of the person is 75 kgs, but what is his initial velocity? This kayak is initially at rest, nothing is being provided to us, it is stationary, so no velocity, it is not moving. So it means if this is at rest, so this will be velocity 0, 0 multiplied by anything is 0, so this vanishes. Kayak is also at rest, it is stationary, so rest. This is also stationary, so all three of them are 0. Now on the other side, we wanted to find out that this person who is sitting in the kayak, with what velocity he will move once the harpoon is thrown with the velocity of 12 meters per second. Obviously he's going to move in the opposite direction because of the Newton's third law. And now this person is sitting in the kayak, so I can write it as m1 plus m2, because both of them, kayak and the person, will move with the same velocity, times v final plus m3 v3. M3 is equal to m3 is equal to 0.72 kgs. So I'll mark it as 0.72 multiplied by velocity. Velocity is 12 meters per second, which is towards the right. And then I will try and simplify these questions. Once you're going to simplify this question by multiplying them together, So this goes on the other side, 0.72 multiplied by 12, and this becomes negative equal to, this is 75 plus 10, 75 plus 10 equal to V final. I'm just running out of the space for this question. And then this becomes 85, dividing both sides by 85. 85, that's going to give me the V final. So V final, I'll do it down here. V final will come out to be 0.1016. This is negative. So towards the left hand side, I can call it as final velocity is equal to 0.01, 0.10, sorry, 0.1, not 0, this is 0.101, so 0.1016 meters per second towards the left side. So hopefully you were able to understand this question, and I'll see you with another video for the two-dimensional problems. If you want to subscribe this channel, that will be a great help. Thank you very much. Bye now.